Hey guys, this is Vaishak Pillai and welcome to Embedded In. This session is an introduction to cryptography. We're going to be introduced to some essential concepts of crypto that we will be using throughout the session. And this is intended to make you aware of some of the basic concepts which you can take back and apply to any secure system that you're building. These are going to be discrete concepts which is going to tie together at the end of the session. So be patient and follow along. The first thing that we want to understand is something called base64 encoding. So very often we have a lot of binary data that is being generated within systems, and typically the way to store this is as a binary file itself. But when you want to transmit this over a network or want to process this in a different system with a different architecture, especially if the architecture is different in terms of the NDNS, then this can mess up the way the data is perceived and processed. To work around this, especially to transfer binary data over networks and across systems of different architectures, there is this system called base64 encoding that is introduced. If you go to the Wikipedia page for base64 encoding, you'll see that there is a table which maps 6 binary digits into a character. This is the basis of base64 encoding. If you have a stream of bits, say 1010110, 11101110, then what you do to get this encoded in base64 is first segment this into groups of 6 bits and map this to the value in the table. So in this case we have 101011 which maps to R. So in base64 encoding, this will be represented by the ASCII character R, and so on and so forth. To see this in action, we can use the base64 command which is available in all Linux systems. So let us echo a string hello into the base64 command. Base64 command typically takes a file as an input. So to get a string across, we are doing this. So we see that it has been encoded into A, G, V, S, B, etc. So to confirm our initial learning, let us do this manually. Let us pipe hello. I'm passing the -n to avoid the terminating characters, and pipe this to XSD with a -b flag to see the binary representation. Oh, I should have given the -n at the beginning of the command. So this is hello, HELLO. Let's copy this and start processing this manually. Alright, I have the string that we converted to binary. I also have the base64 representation here for our reference to make it a bit easier for us. So first let us take the first 6 bits, 1, 2, 3, 4, 5, 6. So it is 011, 010. So 011, 010 will map to small letter A or 26 as we can see here. So this will be A. The next 6 bits are 000110 which maps to G here. Then we have 0101011 which maps to V here. So as you can see, even though the string hello had a proper ASCII representation, each of the ASCII will be 7 bits or 8 bits. When we are doing a base64 transform, this ASCII representation is not honored at all. We will look at the binary representation of how a system would see the string hello and map the bit stream into a base64 mapping table. Now because it was ASCII, it would look a bit stupid to do this because the whole representation was being changed. But assume that this was a binary stream of data that is coming in from, say, a sensor or a binary file. Now, this representation is a foolproof way of mapping this binary data into something that can be transferred over the network. The second concept that we are going to learn is called hashing. So hashing is a very familiar concept for programmers, where we convert an input of arbitrary length into an output of fixed length. This fixed length output will always be unique, or at least that is a requirement of the system. This is also often called a digest, because you're taking a very long string or a very long input and converting that into a small digested piece which is of fixed length. Again, we can see this in action. Let us pass the string hello to the SHA-256 sum command. A 256-bit representation of the input is generated. The interesting point to note here is that even if I increase the length of the input, the output is always going to be of a fixed length, meaning I can have a unique representation of a very large input by just using the hash. Of course, there are concepts of collision and collision avoidance and entropy and all that comes into picture here, but we're not going to talk about all those complexities here. The main idea to understand here is that we can represent an input of any arbitrary length with a fixed length unique output. Meaning, for example, if you feed in the entire works of Shakespeare to a SHA-256 sum algorithm, it will generate a 256-bit unique representation or a digest of all the input that you gave. So in a way, you can say that the entire works of Shakespeare is contained within this 256-bit representation. A change to even a single word or a single alphabet or a character or addition of a new space to the input will change the SHA-256 sum that you're seeing here. There are different hashing algorithms available. We will see that a bit in detail when we generate some certificates and all that. But this concept of a digest is what you need to understand. The next concept that we are going to talk about is encryption and decryption. Essentially, consider the operation of encryption or decryption as a black box. We give it an input, which we call as the clear text. We feed it a key and we get an output, which is called the ciphertext. So you feed in that clear text along with a key and you get a ciphertext. The property here is that the ciphertext cannot be converted back into the clear text without the use of the key and the decryption algorithm. Unless you have the key with you, you will not be able to decipher the output and make meaningful sense of the output. This is the very top level concept of encryption and decryption. Why we talked about this is to talk about a very specific concept of symmetric and asymmetric cryptography. In symmetric cryptography, the operation is very much similar to what we just talked about. There is a single key that can be used for encryption as well as decryption. Whereas, in the case of asymmetric cryptography, we always have a key pair. A key pair consists of a public key and a private key. And depending on the operation that you want to perform, you can use one of this for encryption and the other for decryption. But the primary point to note here is that the private key should always be kept as a secret and should never be shared even to the receiver of the message. It should always be kept safely by the person doing the encryption. There are different operations where we use this. We will soon see an example of signing a document with a private key. But finally, the key point to note here is that the public key is the only thing that should be sent out to people, and private key should always be kept safe. It might be a bit confusing to see that we are publishing a key for open access. We will soon see where it is useful, but this is the key concept to understand here. Alright, so let's see symmetric key cryptography in action. We will choose AES as the algorithm that we want to use here. AES is a symmetric key cryptography algorithm that is widely used in TLS today and many other places, of course. So What we will do is we will first create a text file with a string in it, encrypt it, and try to decrypt it again with the same key. Let's first create a file. Let's call it as clear text, and we are going to echo a string hello with, let's put the -n flag here, and pass it on to clear text. So we can see here clear text has the string hello in it. What we're going to do next is encrypt it with OpenSSL. Let's say OpenSSL encrypt, and the cipher that we're going to use is AES-256 in the CBC mode. So CBC. Instead of the key, we are going to pass a password here. I passed an embedded in. So internally what happens is, using a spec called the PKCS5, this password gets converted into a key that can be consumed by the AES algorithm, and then that will be used to encrypt the file. The input in this case is clear text. The output is going to be ciphertext. A new file will be created, and let's put the -p flag so that we get to see the intermediate key that is created by PKCS5. What did I pass extra? Let's see. Oh. That should be pass. Okay. So there are 3 parameters derived out of the password that we gave. It is a salt, a key, and an IV. IV is initialization vector. We are not going to go into the details of all this, but the only thing that you need to decrypt the encrypted file, which is ciphertext in this case, if you see ciphertext, it is a garbled bunch of data which is nowhere close to the clear text hello that we passed in. Now we want to generate that input back from this garbled text, which is the encrypted text. For that, we use the same command, but just that we tell the enc command that it is going to be a decrypt, and the in file is the ciphertext, and let's call the out file as decrypted text. So same password, so the same key, salt, and IV is generated. There is a mechanism by which you can store these parameters into a key file and then pass the key file and all that. We are not going to go into those details. We will see that, however, in the next section when we are going to understand asymmetric cryptography. So, moment of truth, we are going to see the content of decrypt. It is hello. Now, had I passed a wrong password here, suppose I did not know the password and I'm giving it as a password, a different key and a different salt and IV will be created based on this password. And you will see that OpenSSL himself is complaining that this is a bad decrypt. So if I dump the data in decrypt file, okay, there is nothing created here. But at times it can be the case that output is generated, but that is going to be some other garbled data which is nowhere resembling our input data. So this is AES. This is how symmetric cryptography happens. Now let's take a look at asymmetric cryptography. Before we see asymmetric crypto in action, one concept that you need to understand is that of one-way function or a trapdoor function. So that is a mathematical operation which can happen only in one direction, and from the output you will not be able to generate the input back again. What we did with hashing or digest was an example of that. By seeing just the 256-bit hash, you will not be able to generate the input. A similar concept is used in asymmetric cryptography when we talk about private and public key pairs. If we have access to a private key, we can generate the corresponding public key, but doing it the other way around is not possible. We will see this in action now. When dealing with asymmetric cryptography, we can use either RSA or EC. EC being elliptic curve cryptography. These are two of the most common or famous algorithms that are used in the scenario of asymmetric cryptography. We are going to look at EC mainly because a 256-bit EC key is cryptographically as strong as a 2048-bit RSA key. EC is also very efficient when implemented in hardware. So this is a favorite for all embedded systems. There are very efficient, tiny hardware crypto modules that we can buy out there, which does elliptic key cryptography with secure key storage and a lot of bells and whistles at a very low price. ECC608 from Microchip is a good example of such a device. So let's see this in action. So the first thing that we are going to do is to generate a private key. For that, we use again OpenSSL with ecparam as the command. And the name of the curve that we are going to use is prime 256 K1. So there are different curves that can be used to do elliptic curve cryptography. We are not going to go into the details of that, but these are different mathematical curve models that you can use to perform the crypto operations. In this case, we are going with the P256 curve. We are going to generate a key. So we say gen key, and we're going to store the output in private.ec.key. I'm just giving it a name. Sorry, it should be V1. Again, it's a typo. K1. Sorry. I was recently working with some of the K1 algorithms, so I got a bit confused with that. But yeah, prime 256 V1, as I initially told, is what we should be using. So we have a private key. So what you see here is the base 64 encoded version of the private key. So we looked at base 64 in the beginning. The private key as such is a 256-bit value. And we have some more parameters like modulus and prime that we have to store inside the key for it to be useful. All that is stored in a specific format as specified by the RFCs, and it is converted into a base 64 representation so that it can be stored and manipulated using text files. What you see in the beginning is the EC curve parameters to indicate that this is a key for a prime 256 V1 curve. If you want to avoid that, you can give the no out parameter, and the curve parameters will not be part of the private key. It's up to you. Now the next step for us is to generate a public key corresponding to this private key. For that we do OpenSSL. We're going to use the EC command. Input is the private key and pubout, or the public key output, is the operation that we're going to do. And we're going to say the output can be in public.ec.key. So he read the initial key we had in the private key file and generated a public key. So we have the public key as well here. Let's leave it there and get into an operation that we can do using this private and a public key. So there is this concept of a digital signature. Typically we sign on a document when we agree to all the terms that are written there, and it is an assurance that the content of the document is agreed upon. Now the problem with physical documents is that the contents can be tampered with later on, and a digital signature is something which we use to avoid that from happening. What we do to generate a digital signature is, when we have a document, consider that it is a PDF. First we compute the hash or the digest of this document. So irrespective of how long the document is, we get a fixed length representation. And then, now to sign this document, you should generate a public-private key pair. So we have a key pub and a keep private. What we do is we encrypt this digest using the private key. And the output of this encryption is what we call the digital signature. We attach this digital signature back into the PDF file. So this is going to be a part of the document. And this is what we send to anyone who wants to read this. To verify whether the content of the document has changed after it has been signed, what you do is you recompute the digest as step 1. As step 2, you decrypt the signature that was part of the document, which will give you a digest because it is the encrypted form of the original digest. And then you compare these two items. These two will match if and only if the contents of the PDF has not been altered after the original DS has been created. What you need to understand here is that encryption of the digest can be done only with the private key, and the public key can be used only for decryption. So private key used to encrypt and public key is used to decrypt. You cannot do it the other way around. In the case of symmetric key cryptography, we were able to encrypt and decrypt with the same key, but here you can only do one of the operations with the key. Now, whether you publicize the key used for encryption or the key used for decryption depends upon the scenario. In this case of a digital signature, we are publishing the public key, telling to the world that any document that comes from me will be signed with my private key, which I keep safely. If you want to verify the authority of the document, you can use my public key, which is well known, which I'm publishing in public domain. You can use that to verify my signature. So let us see this digital signature signing and verification in action using the public and private keys we just created. We will use the OpenSSL digest command, DGST. We are going to use a SHA-256 hash, and we are going to sign it with the private key that we created. And the output is going to be, let's say, signature, and the input can be the, let's say, the clear text, the hello text file that we created before. So I have clear text which says hello, and I have the signature. Let's do a XSD. Yeah. This is the encrypted digest of the string hello that came in from the clear text. There are different mechanisms of attaching a signature to a file. For a container format, it is very easy. For PDF, they have their own mechanisms. Now, let us assume that I just pass on the clear text and the signature as separate entities. For a receiver, if he wants to verify whether the contents of the file has been changed, they can use the OpenSSL digest command. Again, DGST. It's a SHA-256, so that parameter should be known. And I'm telling verify using the public key. So I have to pass 3 parameters. I have to pass the clear text, or to the reader, I have to give the clear text, the signature, and the public key, and of course the the hashing algorithm that has been used. The signature is in signature file, and the input, which is the clear text. So it says verified. Okay, everything is fine because we did not alter anything in the clear text file after the signature was generated. Now suppose, assume that we changed something in the clear text. Let's say I added a extra space, as trivial as that. Now if I try to verify the signature again, it will say the verification has failed. Which means if the integrity of the document has been altered, then signature verification will fail. And if and only if the contents are the same, I can do this. I remove the last space that we added. Save it again. Okay, I would have messed up the content. Let's see. Let's echo back the hello to clear text and verify the signature again. Verification passes. The previous one failed because when we open it in an editor and make changes, the editor would possibly add some stuff into the file. Let us try that again. I added a space. Okay. Let us dump this and Let us make it back to hello and dump this. Yeah, as you can see, there are extra characters added at the end of the file. This is 6F0A and this is 6F. So that is why the signature verification failed. So all the more proof that if the document changes its structure or the content changes, then the signature verification is going to fail. You can see that OpenSSL internally generates a digest of the input by giving OpenSSL DGST, the algorithm, SHA-256, and the input. So as an intermediate step, this digest is generated and then fed into the signing part where the private key is used to sign this hash.
So, to recap, we first learned about base64, a mechanism to encode binary data into ASCII representation. Then we learned about hashing that lets us convert an input of arbitrary length into a fixed length digest. Later we learned about encryption and decryption, and specifically about symmetric and asymmetric key cryptography. During that discussion, we also talked about key pairs and one-way functions. Finally, we brought all these concepts together while discussing digital signatures, which is essentially an encrypted hash in base64 format. Thank you for watching and have a nice day.